Let's go on now and see why astronomers like to observe objects at many different wavelengths of the electromagnetic spectrum. We have telescopes that run from radio telescopes up through gamma ray telescopes and every part of the spectrum in between. So you may wonder, why do we bother with that? I'm just going to show you why using a map of the entire sky. So this picture here is a picture of the entire Milky Way. The guy who took the picture had to use several cameras in both the northern hemisphere and the southern hemisphere, and it took him many nights to make this entire map of the Milky Way. And what he has done is he's put the center of the Milky Way in the center of the image. The band of the Milky Way goes flat left to right across the image. Let's point out some of the features that we can see in the Milky Way. So because we've centered this picture on the Milky Way itself, the North Star is not at the top. The North Star is actually off to the upper left, and you can't see it on this image. It is there, but you can't see it. The dark patchy regions you see across the Milky Way are dust. Now you probably have noticed that if you let dust build up on your windows, whether it's the windshield of your car or the windows of your house, you get too much dust and you can't see out very well. That's because dust is very good at absorbing optical light. This is dust in our Milky Way out in space that's blocking light from more distant stars from getting to the Earth. When we go to some of the other wavelengths, you will see that not all wavelengths of light are blocked by dust, but dust is very good at absorbing visible light. Some objects that you may have heard of before are noted below the Milky Way: the Pleiades star cluster, the Andromeda galaxy, the Large and Small Magellanic Clouds. You may not have heard of them. They're only visible from the southern hemisphere, but they're satellite galaxies of the Milky Way. The Orion Nebula is there on the right. And as I said, part of this you can only see from the southern hemisphere. So this oval sort of indicates what you would need to go south of the equator to see. So north of the equator we can see everything that's not in that oval region. So let's start at the longest wavelength, radio waves. Radio waves in our galaxy mostly come from particles trapped in magnetic fields. Stars, supernovae, even the galaxy itself all have magnetic fields. When particles like electrons or protons get caught in those magnetic fields, they emit radio waves. And so what you see here are radio waves coming from magnetic fields in our galaxy. This is a false color image, so yellow light is the brightest radio waves, red light are the fewest radio waves. And what you see is that there are a lot of radio waves that come from the very center of the Milky Way, and then it gets a lot fainter very quickly, but you also see these big looping structures that we can't see in optical wavelengths of light. So we can learn about lots of different types of structures in our galaxy by looking at radio waves as opposed to visible light. This map shows the Milky Way in a very particular wavelength of radio light, and that wavelength is 21 centimeters. At 21 centimeters, cold hydrogen gas is very good at emitting light. So when we look at the galaxy in this wavelength, we are seeing where there is hydrogen gas, and since hydrogen is what can make up new stars in our galaxy, we can tell where there may be new stars forming. And again, you see here in this particular picture, dark red means lots of radio waves, dark blue means very few radio waves. You see that most of the 21 centimeter radiation comes from the band of the Milky Way, and there are a few looping structures. You can see that the Large and Small Magellanic Clouds have a lot of hydrogen as well, and there's even a little faint tail that goes between them because they recently passed by each other and pulled some gas out. We'll learn about galaxy collisions in the near future. So 21 centimeter light is a very special wavelength that allows us to learn a lot about where stars may form in galaxies. If we go shorter into microwave light, we're changing color schemes again. Here red is a lot of microwaves, blue is very few microwaves, and you still see the Milky Way across the middle of the image with lots of microwaves coming from there. Microwaves originate from objects that are near absolute zero in temperature. So this would be the absolute coldest stuff in our galaxy is in that band across the middle. The microwaves that you see from outside the band of the Milky Way are actually coming from the Big Bang. As we will learn at the end of the class, the Big Bang created a lot of heat energy in the universe, and over time the universe has cooled off so that the universe itself is now just 3 degrees above absolute zero. And so that patchy, spotty stuff that you see here above and below the Milky Way are the most distant light that we can see in our universe coming from the very edge. And we'll talk about how we know that again at the very end of the class. We now move into far infrared light. So this is that wavelength of sort of 1 millimeter to 1/10 of a millimeter, where we need to go above Earth's atmosphere to see it because the Earth's atmosphere glows in this light. And that's because warm objects, room temperature objects, glow in far infrared light. So this was created by a satellite. Here white means lots of far infrared, dark means little far infrared. Those little gashes that you see sort of just below the middle left and in the upper right, that's where the satellite didn't take any information. And the Milky Way itself is very visible. You can see the large and small Magellanic Clouds below and to the right of the Milky Way. You can see that where the Orion Nebula is, that there's a lot of warm objects there. That's where new stars are being formed out of that very cold gas, and as it forms into stars, it begins to warm up, and at some point it reaches this magic temperature. That sort of S shape that you see that goes from the lower left up through the center and to the upper right, that is our own solar system. We have dust in our solar system from comets and from the collisions of asteroids. They tend to orbit the sun in the same plane as the planets, and because of the weird way we've mapped out the Milky Way here, instead of being a flat band, it has this funny S shape. We now move on to near-infrared light. Near-infrared light is shorter wavelength than the far infrared we were just looking at, but it's longer wavelength than what our eyes can see. So this is wavelengths of around 1,000 nanometers to 1/10 of a millimeter or so. And near-infrared light comes from cool stars, objects of around 2,000 or 3,000 degrees. Near-infrared light is also very good at going through dust. So you still see some dust in our Milky Way here, but you don't see nearly as much as in optical light because the near-infrared light can make it through. So often when we want to study what's going on in dusty galaxies, we use near-infrared light because that light can reach us on the Earth. But when we're looking at near-infrared light, we are looking at stars, just like we tend to in the optical. So again, moving shorter in wavelength, higher in energy, this is that same optical light picture we saw earlier. Just again, reminding you what it looks like. Optical light tends to come from stars, like the sun, other stars because we see them, and also in occasions from energized gas, like the Orion Nebula. We don't have any pictures of the Milky Way in ultraviolet light. Ultraviolet light does not make it to Earth's surface, so you need satellites, and the satellites that we've launched have never made a full map of the universe in ultraviolet light. Ultraviolet light tends to come from hot stars, much hotter than the sun. So let's just skip over that and go to X-rays. This is a picture of the Milky Way in X-rays. In this image, blue and yellow mean lots of X-rays, red means fewer, and black means very few X-rays. And you see that the sky looks very different in X-rays than it has at any other wavelength. You see this big looping structure at the middle, but where we would normally expect to see the Milky Way, we don't see anything special. Now some of that's because X-ray light can get absorbed by dust, just like optical light, but the main reason is that X-ray light comes from gas of millions of degrees, and our galaxy just doesn't have a lot of that gas. The structures that you see, the big circle in the middle, the little loop off to the left-hand side, these are the remnants of stars that exploded as supernovae many, many years ago, and that gas is very energetic and very hot, and so we can still see it glowing today. In fact, we don't see this gas in the visible light at all. We must go to the X-rays to study it. Finally, the shortest wavelength light is gamma ray radiation, and here we go back to a color scheme where yellow means very bright, blue means very little gamma rays. Gamma ray radiation comes from very energetic processes such as black holes or neutron stars or very violent collisions of gas. And so there are very few sources. Most of what you see in the Milky Way are neutron stars and black holes in the Milky Way. And most of what you see outside of the Milky Way are very distant galaxies that have gigantic black holes at their centers and are gobbling up tremendous amounts of gas. And they emit gamma rays. Hopefully you've seen why we look at the Milky Way in lots of different wavelengths of light, because at different wavelengths you see different physical processes, and we can study objects in the radio that we cannot study in visible light. We can study objects in gamma rays that we cannot study in radio or visible light. And so by picking the appropriate wavelength for the object we want to study, we can focus in on those objects very easily. This concludes Mini Lecture 2. Please proceed and complete the response to Mini Lecture 2 that's available on eCollege, and then go on and watch Mini Lecture 3, where we will talk about thermal radiation.